So determination of standard reduction potential of an electrode. Okay, how to determine the standard reduction potential? See, we have already discussed about the reference electrode. Okay, the reference electrode that we are going to use here is She, means standard hydrogen electrode. Okay, and for standard hydrogen electrode, if you use standard hydrogen electrode as anode, at anode oxidation takes place, so H2 become H plus. H2 become H plus is called oxidation. Oxidation potential is 0 if you use hydrogen electrode as anode, standard hydrogen electrode as anode. If you use standard hydrogen electrode as cathode, then H plus ion undergoes reduction and become H2. Standard reduction potential also 0. Standard oxidation potential as well as standard reduction potential both are 0 for the standard hydrogen electrode. You can use it as anode or you can use it as cathode, whatever it is. Right then. So this point is very important, student. This is very, very important. Listen. Standard oxidation potential for hydrogen electrode or standard reduction potential for hydrogen electrode is 0. But sometimes students confusing with this. What's the value of this potential? This is not standard potential. If you put not symbol, then only it is standard. Okay. This is simply hydrogen electrode potential. Hydrogen electrode potential is not 0. Students, observe carefully. Very important point. Only standard hydrogen electrode potential is 0, not just hydrogen electrode potential. Okay. When you say a hydrogen electrode is standard hydrogen electrode, if the pressure used is 1 bar, if you use 1 bar pressure of hydrogen gas, and if the concentration of H plus ion, or I can say activity of H plus ion is 1 molarity, okay, and temperature is not important, but by convention people use this temperature. This is not that important. Okay, only these two are very, very important. If you maintain pressure as 1 bar and H plus concentration as 1 molarity, and conventionally people use 25 degrees Celsius. So if you fix all these three, then the hydrogen electrode becomes standard hydrogen electrode. Okay, remember this is very important. When you fix pressure as 1 bar, H plus ion concentration 1 molarity, and temperature, by convention temperature is 25 degrees Celsius. If you fix these three quantities, then hydrogen electrode becomes standard electrode. For standard hydrogen electrode, the potentials are 0. Okay, if it is a simple hydrogen electrode, suppose if the pressure is not 1 bar, instead of 1 bar if I have 2 bar pressure, then hydrogen electrode potential is not 0. Suppose H plus ion concentration is not 1 molarity, instead of 1 molarity if it is 1.5 molarity, then it is not standard hydrogen electrode. Only for standard hydrogen electrode these potentials are 0. Keep this in mind, very, very important. Okay, now using the reference electrode we are going to determine the potentials of the other electrode. Yes, how to do that? Now let me take for example we'll take zinc electrode. Okay, now our goal is to find what is the standard reduction potential of zinc. Standard reduction potential of zinc. Okay, how to determine this value? What to do? You take this electrode, connect it with the hydrogen electrode. Okay, so let me write in the next page. Students, observe this carefully. It's actually very simple. What we have to do? You take a zinc rod and immerse it in a solution containing 1 molar zinc sulfate. You take 1 molar, because we are going to measure standard reduction potential, so we should take 1 molar concentration and immerse a zinc electrode in this. So this is zinc plate, zinc solid, and here solution contains zinc ion of concentration 1 molarity. So this is zinc electrode, and let the temperature be 25 degrees Celsius. We should maintain temperature as 25 degrees Celsius. Okay, this is one half cell or one electrode. Now we need to find the potential of this electrode. So what I'm going to do, I'm going to connect this with some reference electrode. Okay, how to do that? So what's the reference electrode we use? Standard hydrogen electrode. For standard hydrogen electrode, I'll take a container in which we'll take some solution in which H plus ion concentration or activity, we are supposed to use activity, but solutions normally we use dilute solution, so H plus ion concentration is 1 molarity. If you use dilute solution, activity and molarity are almost equal. Okay, so I'll use H plus ion concentration as 1 molarity. Instead of activity, I'm using molar concentration. Okay, and immerse a glass tube, which we discussed in the last class, and here there is a valve. Through this valve we pass pure and dry hydrogen gas at 1 bar pressure. We should pass pure and dry hydrogen gas at 1 bar pressure, and here a electrode is fused, a platinum electrode is fused at the middle, and here we have one wire connection. So this is nothing but, and let the temperature of this solution also 25 degrees Celsius. So both the solution temperatures are 25 degrees Celsius. Concentration here also 1 molarity, here also 1 molarity. Here pressure is 1 bar. So all standard conditions are maintained. Okay. Now what I'm going to do, I'm going to connect the two electrode externally using a potentiometer. So this is a potentiometer. Let us assume like that. Okay, I'll connect the wires to the potentiometer. So this is nothing but potentiometer. We are not supposed to use voltmeter because voltmeter will consume some current. Okay, therefore we avoid voltmeter to measure the cell potential. So whatever potential that appear here is nothing but cell potential. So we have connected the wire, two electrode externally, and we have to connect the two solutions using salt bridge. So I'll connect the two solutions using salt bridge. Okay, this is the salt bridge. Once you connected these two, some potential will appear here. That is nothing but standard cell potential that we can measure. We can measure the standard cell potential. Right? Here, students observe carefully. Zinc undergoes oxidation and reduction occurs at the hydrogen electrode. Okay, zinc will undergo oxidation. Therefore, this is the anode. This is the anode and this is the cathode. Okay. So, you know very well, the formula for standard cell potential is standard reduction potential of cathode. Standard reduction potential. Reduction means H plus become H2. Standard reduction potential of cathode minus standard reduction potential of anode. So outright reduction potential E naught, zinc 2 plus becomes zinc. Okay, the difference between these two is nothing but cell potential. We can determine this experimentally, okay, using the arrangement. Okay, this arrangement, that is whatever potential that appear in the potentiometer, it is nothing but standard cell potential. Okay, and what's the value of this? Since it is standard reduction potential, standard hydrogen electrode reduction potential, this value is 0. So this nothing but E naught, zinc 2 plus becomes zinc. So now students observe carefully. Since this is 0, so whatever potential that appear in the potentiometer, okay, you just change the sign of it, you will get the standard reduction potential. Therefore, the standard reduction potential for zinc 2 plus becoming zinc is equal to minus E naught cell. Minus E naught cell. Right? It's very simple actually. right? So you can measure what is the standard reduction potential of zinc electrode, okay, by connecting it with the standard hydrogen electrode. So whatever cell potential that appear here, okay, you take the minus of that, you will get the standard reduction potential of zinc, okay. And the exact value for zinc, it is minus 0.76 volt. This you may be last class, I think 2 class before we discussed that the exact value is minus 0.76 volt, standard reduction potential for zinc. Okay, this is the experimental value. Experimentally the value is 0.76. okay, change the sign, so you'll get minus 0.76 volt, right? In this manner you can determine, okay, you can determine the potential of any electrode, okay, students. Okay, so by using this technique you can determine the standard reduction potential of any electrode, okay. But what is the problem with the standard hydrogen electrode is that every time you have to use pure and dry hydrogen gas, and you have to maintain the pressure as 1 bar, which is a tough task. Maintaining 1 bar pressure and getting pure hydrogen gas, these are all some difficulties, okay, exist with the use of standard hydrogen electrode. That's why people prefer calomel electrode, okay. Calomel electrode is the secondary electrode. The construction of calomel electrode is somewhat easier, okay, so keep that in mind. But this is the primary reference electrode, no doubt in that. Then, so in this way you can determine the standard reduction potentials of electrodes, okay. Now once we determine this, what we can do now, we have the values of standard reduction potentials, okay, for many electrodes, okay. Now using the standard reduction potentials, right, what we can do, what is the significance of these values, okay, students. Before going to see that, let me give this point and I'll make it things much clearer. Students, observe carefully. When metal become metal ion and release electron, this is called oxidation, okay. So here metal becoming metal ion, okay, this is called oxidation potential. If I put not symbol, it is called standard oxidation potential of the metal, right? Suppose if the metal ion gains electron and become metal, this is called reduction, and here the potential M, metal ion becoming metal, it is called reduction potential. If I put a not symbol here, it is called standard reduction potential. So while writing the potentials, you should be very, very clear. When metal become metal ion, it is oxidation, so this potential is oxidation potential. When metal ion become metal, it is called reduction, and this potential is reduction potential. And the not symbol indicate it is standard oxidation potential and standard reduction potential. And remember, what is the relation between these two? Standard reduction potential and standard oxidation potential. What's the relation? Very simple. Standard oxidation potential. What's the relation? See, you just change the sign of one. Suppose you take oxidation potential, change the sign, you will get the reduction potential. Okay, you take standard oxidation potential of one electrode, change the sign, you will get the corresponding reduction potential of that electrode. Okay, so remember this is very important. Now we'll see what are the significance of the standard electrode potentials, right? Significance of standard electrode potentials. What are the significance of standard electrode potentials? Okay, significance of standard electrode potential. Okay, what are the significances? Number one. Students, using these values, okay, you can calculate, right, standard cell potential of any electrode, any cell. Okay, E0 cell standard cell potential can be calculated. What's the meaning? Suppose I'll take two cells, two half cells. Say, for example, let me give two half cells like this. I'll take cadmium solid immersed in cadmium 2+ ion aqueous solution. Okay, double bar indicate that the double vertical line indicate salt bridge. In the other side, I'll use AU3 plus aqueous becoming AU, right? AU solid, gold, right? See here, this left hand side part is the anode and the right hand side part is the cathode. Now the question is, what is the standard cell potential of this electrode, this cell? What is the standard cell potential of this cell? You can determine experimentally, but standard cell potential you can get the value directly by using the standard reduction potentials of these electrodes. Standard reduction potential values are available for all the electrodes nowadays. Okay, see, for cadmium, the standard reduction potential for cadmium 2+ becoming cadmium, the value is, for cadmium, the reduction potential value is -0.4 volt. -0.4 volt. And standard reduction potential for gold, AU3+ becoming AU, right? For this, the standard reduction potentials are available, which is +1.50 volt. +1.50 volt. So these potentials are available. Students, observe carefully. Standard reduction potentials of the electrodes are available. Using this, okay, you can calculate standard cell potential without doing any experiment. You need not do any experimental work, okay, because these values are available. So if you know standard reduction potentials of the electrodes, you can calculate standard cell potential directly. How? Very simple. You know the formula, right? What is the formula? Standard cell potential equal to standard reduction potential of the cathode. I'll write here. Standard cell potential is equal to standard reduction potential of the cathode. Cathode is gold here, so AU3+ become AU, minus, that is right hand side electrode, standard reduction potential of the right hand side electrode, minus standard reduction potential of the left hand side electrode. E0 cadmium 2+ becoming cadmium. Students, observe carefully. I'm considering only reduction potentials. Okay, and here also only reduction potentials are given, right? Copper 2+ become, sorry, cadmium 2+ becoming cadmium, reduction potential. Gold 3+, AU3+ becoming AU, reduction potential. So the values given are reduction potentials. Okay, if the potentials given are reduction potentials, then you can use this formula directly. Okay, is equal to, what's the value of this? The value is given +1.50 volt, and here we have minus sign here. And what's the potential of this? -0.4. So 1.5 plus 0.4, okay, you'll get 1.90 volt, right? This is the cell potential of this cell. See, we didn't do any experiment. Okay, I'm not getting this value experimentally. I am just calculating the value by using this given standard reduction potentials. So if standard reduction potentials values are given, you can calculate the standard cell potential directly. Students, you should be very clear here. I am not saying that you can calculate cell potential. No, you cannot calculate cell potential. Okay, to calculate cell potential you require something else. To calculate standard cell potential, yes, it is easy. You can use the standard reduction potentials of the electrode and you can calculate. Okay, to calculate cell potential, you know very well the difference between cell potential and standard cell potential. Standard means you should maintain concentration as 1 molarity, pressure as 1 bar, and by convention temperature as 25 degrees Celsius. Okay, if the values are different, then it is cell potential. For cell potential, you can calculate cell potential by using some different technique. We are going to discuss that as we go along. Okay, so this is first important significance of standard electrode potential. If you know standard electrode potentials, you can calculate standard cell potential without doing any experiment. Okay, then second one, if you know the standard cell potential, the standard electrode potentials, okay, you can identify whether a particular reaction takes place or not. Say for example, hello?
Sir, can we use this method for any cells?
The second important application is that suppose standard reduction potential values are given for some electrodes. So second application, we can identify or we can compare. If 2 or more elements are given, we can compare which one can act as a good reducing agent or which one can act as a good oxidizing agent. Okay, we can compare reducing agents, reducing property, okay, or we can compare the reducing ability or property or oxidizing property. Of an element among the given elements. Okay, how to do that? Students, this is very, very important. Keep this in mind. Suppose I'll give standard reduction potential for some element, SRP. SRP means standard reduction potential. If standard reduction potential is negative, students observe carefully. See the value. If the value is negative, then that metal ready to undergo oxidation, or that metal undergo oxidation readily. It releases electron and become metal ion. Students observe carefully. If SRP value is negative, that metal ready to undergo oxidation. If SRP value is positive, standard reduction potential value is positive, it means that metal ion, the metal ion gains electron and undergoes reduction readily. Very simple. If SRP value is positive or high, in general you can say high, if SRP value is high, then that metal ion undergoes reduction readily. If SRP value is negative or low, okay, I can say in the other way, if SRP value, standard reduction potential value, if it is high, okay, among the given species, if SRP value is high for a particular species, that means that species undergoes reduction readily. Okay, high means positive. Or among the given elements, you see which one has highest SRP value. Okay, the element having high SRP undergoes reduction readily. If metal ion undergoes reduction, that means it is gaining electron, right? It is gaining electron. That means that element can act as an oxidizing agent, right? Or we can say that metal can act as a oxidizing agent, OA. I'll put OA. What is OA? OA means oxidizing agent here. That element can act as an oxidizing agent. I repeat, see the SRP value. If SRP value is high, then that element, that metal ion undergo reduction readily. Okay, that means it is gaining electron. It is gaining electron. It is gaining electron from some other species. Students, observe carefully, this metal ion gaining electron from some other species. That species will undergo oxidation. That's the meaning. So this metal ion oxidizing some other species, so it can act as an oxidizing agent. Suppose if SRP value is low, what does this indicate? It indicates that that metal undergoes oxidation readily. Oxidation readily. It means the metal can donate electron. If the metal donates electron, that is, it is donating electron to some other species, so that that species undergoes reduction. So that metal can act as a good reducing agent. Okay, you can identify whether a metal is a good oxidizing agent or a good reducing agent, okay, using the SRP values. Right, just for understanding purpose, I'll give some values, values for some metals. You try to tell me which is a good reducing agent among this. Okay, let me give few metals. Say for example, I have I'll take calcium, I'll take cadmium, I'll take nickel, and I'll take copper. Now the question is, among these, which one can act as a good reducing agent? Good reducing agent. Good reducing agent. You need to identify that. Listen, students, I'll repeat once again. For a metal to act as a good reducing agent, SRP value should be low. SRP value should be low. Now I'll give the SRP values for these metals. Okay, standard reduction potential values are available. For calcium, the value is minus 2.87. Minus 2.8. I'm giving SRP values. 2.87 volt. And for cadmium, it is minus 0.440 volt. And for nickel, the value is minus 0.25 volt, and for copper it is plus 0.34 volt. Yeah, students, can anyone tell me which is okay? So here calcium is the good reducing agent because the reduction potential is lowest. Now the next question is this: I have given 4 elements and the SOP values are given. You need to identify the better reducing agent or the good reducing agent among the 4. The SOP values are given. What you have to do, first you find the SRP values. What is the SRP value? Just change the sign, that's all. Minus 1 volt, minus 2 volt, minus 3 volt, minus 4 volt. Now see, among these 4, which is the lowest value?
Minus 4.
Minus 4. Therefore D can act as a good reducing agent, right, among the 4. Okay, is this clear, student? Any doubt? So the next question, I have given few species here and the corresponding SOP values. You need to identify which is a good oxidizing agent among these 4. Yes, how to do that?
Lithium, sir.
If SOP value, standard oxidation potential values are given, what you have to do, you convert that into SRP. SRP. Okay, SRP means plus 2.87, plus 1.36, plus 1.51. This is minus 3.05. Am I right? I have told you, if standard reduction potential is lowest, okay, then that element, see, if standard reduction potential is low, that element can act as a good reducing agent. But now the question is, good oxidizing agent. For a metal to be good oxidizing agent, SRP value should be high. Okay, among the three, which one has high SRP value?
Fluorine.
Fluorine. So fluorine, okay, among these four, fluorine is a good oxidizing agent. Okay, so this is second application. Now I'll show you the third application. You can identify whether a particular metal can displace H plus as H2 gas from an acid. Okay, then what's the idea? We can compare, or we can identify metal that can displace, which metal can displace right, H plus into H2 gas from an acid. You take some acid contain H plus. Okay, which metal can displace H plus from an acid into H2 gas? That you can identify using the standard reduction potential values. Okay, yes, how to do that? See, suppose, students observe carefully. I'll take dilute sulfuric acid in a container. I'll take dilute sulfuric acid. So sulfuric acid contain H plus ion. Now I'm going to put some metal here. I'm going to put some metal. So assume that I'm going to put some metal. Which metal can displace H plus into hydrogen gas, or which metal produce hydrogen gas? Okay, when the metal is added in a in dilute acid, dilute sulfuric acid very specifically. Students observe carefully. Standard reduction potential for H plus becoming H2. It is nothing but standard hydrogen electrode potential, right? This is 0, you know very well. This is 0. This value is 0. If any metal has standard reduction potential less than this, okay, standard reduction potential, any metal, you take any metal and this SRP value. See, I am taking only SRP value. Student, observe carefully. If any metal has SRP value less than H plus, less than SRP of H plus, then that metal can displace H plus into hydrogen gas. Okay, then this metal, then the metal can displace H plus into H2 gas. Right? It's very simple. Now listen, student, I'll give few examples. See, I'll take dilute sulfuric acid. Among the four, you try to tell me which one can displace, or which one can displace H plus from H plus into hydrogen gas, right, among these. Okay, let me give few metals. Copper, then I'll give manganese, then I'll give magnesium, then I'll give sodium. Question, I'll give the question like this: among these, which one cannot displace H plus? Which one cannot displace H plus into H2 hydrogen gas? Right? How to identify that? Very simple. See their reduction potential values. Okay, E naught value for copper, I'll write copper 2 plus into copper. This is the reduction potential for copper, and the standard reduction potential value. These values they will provide in the examination. They will provide the value, but right now I'll give the value for copper 2 plus becoming copper. The value is plus 0.34 volt. Plus 0.34 volt. For manganese, standard reduction potential for Mn2 plus becoming Mn. For manganese, the value is minus 1.18 volt. For magnesium, Mg2 plus becoming Mg. Standard reduction potential for magnesium, it is minus 2.37 volt. Minus 2.37 volt. and for sodium, the standard reduction potential for sodium, the value is available, which is minus 2.7 volt, 71 volt. Yeah. Now standard reduction potential values are given. Students, you try to tell me which metal can displace H plus from dilute sulfuric acid into hydrogen gas. See the SRP value. See, SRP value for hydrogen electrode is 0. Therefore, any metal having SRP value less than hydrogen electrode means the metal should have negative reduction potential. Okay, so among the four, right, these three metals have negative reduction potential. That means these metals can displace H plus into H2 gas when you add the metal in dilute sulfuric acid. Whereas copper has positive value, right? So copper cannot displace. So the correct option is copper. So students, this is very important for inorganic chemistry. Keep this in mind. Whether a metal can displace H plus from acid or not, that you can easily identify. So if I take copper and if I add copper in dilute sulfuric acid, right, can copper displace hydrogen gas? Can this reaction takes place? Copper become copper sulfate and hydrogen comes out hydrogen gas. Is this reaction takes place? No. Why no? Because the standard reduction potential of copper is positive. Standard reduction potential of copper is a positive value. It cannot displace. Right? Whereas if I take magnesium, for example, if I take magnesium and if I put magnesium in dilute sulfuric acid, right, magnesium become magnesium sulfate and H plus comes out as hydrogen gas. This reaction will occur. Why this reaction occurs? Because standard reduction potential for magnesium is negative and the value is minus 2.37 volt I have given. Since this value is negative, therefore this reaction will occur. Is this clear, student? Suppose if I take concentrated sulfuric acid, now I am going to add copper. Okay, this is copper, so I am going to add copper. Now will copper react with the concentrated sulfuric acid? The question is, student, concentrated sulfuric acid is a good oxidizing agent. With the dilute sulfuric acid, this reaction does not occur. But concentrated sulfuric acid is a good oxidizing agent. What it will do? See, H2SO4 undergoes oxidation, gives you SO2 plus H2O, and it will produce nascent oxygen. Sulfuric acid, concentrated sulfuric acid, okay, it is a good oxidizing agent to produce nascent oxygen. This nascent oxygen oxidizes copper into copper 2 plus. Therefore, this reaction will occur. Okay, that is copper become copper sulfate and you will get SO2 gas, right, plus water. You will never get hydrogen gas. See, this is very important. You will never get hydrogen gas. You will get SO2 gas instead. Right? Try to understand what I am saying here. With the dilute sulfuric acid, right, copper does not displace H plus into H2. Even with the concentrated sulfuric acid, copper does not displace hydrogen gas. You will never get hydrogen gas. But since concentrated sulfuric acid is a good oxidizing agent, it will oxidize as copper into copper sulfate. This reaction will occur, but you will never get H2 gas. You will get some other gas. Is this point clear, student? Hello, students? Is this point clear?
Yes, sir.
Yeah, good. Now, in the same line, I'll give one more information. Now, students, see, I'll take copper. I'll put copper in dilute HCl, and I'll put copper in concentrated HCl. Can copper displace hydrogen gas from dilute HCl? Standard reduction potential for copper is positive. Therefore, this reaction does not occur. Copper cannot displace hydrogen gas. And concentrated HCl is not an oxidizing agent. Okay, concentrated HCl, right, is not an oxidizing agent. Why? Because here chlorine is in -1 state. Okay, chloride -1 is the least oxidizing state for chlorine. In order to undergo in order to act as oxidizing agent, okay, the chlorine should gain electron. Okay, chlorine least oxidizing state is -1. It is already there in -1 state. It cannot gain electron further. Or I can say simply concentrated HCl is not an oxidizing agent. Therefore, copper does not react even with the con HCl. Okay, what about with sulfuric nitric acid? If we take copper, if we add it into dilute nitric acid, and if we add copper with the concentrate nitric acid, what will happen? Dilute nitric acid, no reaction, because reduction potential of copper is positive. With the same idea, if you use this, student, concentrate nitric acid is an oxidizing agent. Concentrated nitric acid, okay, is an oxidizing agent. It's an OA. OA means oxidizing agent. Since it is an oxidizing agent, it will oxidize copper into copper 2+. So you will get cupric nitrate, CuNO3 twice, and you will get NO2 gas. NO2 gas is liberated plus water. I didn't balance the reaction. Balancing and all is simple. We'll do it later. Okay, under D block element we'll do. Okay, right now you just keep all these things in mind. Okay.
Sir, how to identify an oxidizing agent?
Okay. Can we store? Can sulfuric acid can be stored in a zinc container? Can dilute sulfuric acid store in a zinc container? Zinc container. Can dilute sulfuric acid stored in a zinc container? Yeah, students, can you answer this question? That is, we have a zinc container now. I have zinc container. So this container is made up of zinc. Inside I am going to take dilute sulfuric acid. Is this a correct procedure? Can we store dilute sulfuric acid in a zinc container? Yes, how to answer this type of question? Very simple. You see the reduction potential of H+ ion. Standard reduction potential of H+ becoming H2 is 0, that we know. And see the reduction potential of the container. The reduction potential for zinc 2+ becomes zinc. The value is minus 0.76 volt. I know the value, that's why I am giving. Okay, minus 0.76 volt is the standard reduction potential for zinc. Now, student, if standard reduction potential for a metal, if it is less than H+, in general I can say H+ to H2, if the SRP value of the metal, if SRP of metal, if SRP of the metal is less than H+, see H+ value, standard reduction potential value for hydrogen is 0. Okay, less than 0 means negative, correct? If SRP value is negative, then you cannot store that metal, store sulfuric acid in that vessel. Okay, vessel made up of that metal. Okay, so this is not a correct procedure. Why? Because if you store sulfuric acid in zinc container, what will happen? Zinc will react with sulfuric acid. You will get zinc sulfate and H2 gas. So hydrogen gas will go out, right? And the zinc container starts to dissolve. It becomes zinc ions. So you are not supposed to store. You are not supposed to store dilute sulfuric acid in zinc container. Right? Can we store aqueous nickel sulfate in copper container? Listen, the standard reduction potential for nickel I'll give the values. The values, add the value, 1 second. I've given, yeah. Standard reduction potential for nickel is minus 0.25 volt, and the standard reduction potential for copper, 2 plus becoming copper, the value is plus 0.34 volt. Students, that is, we have a copper container. In this, so the container is made up of copper. Now the question is, can we store nickel sulfate solution in copper container?
Yes, sir.
Yeah, standard reduction potential for nickel and standard reduction potential for copper, you just see. Listen, here standard reduction potential for copper is greater. Therefore you can store this. Why? Because standard reduction potential for the metal is high now. Okay, I'll give in general. In this case, standard reduction potential for copper is high. That means copper cannot displace Ni2 plus into nickel. Therefore we can store. Nickel, aqueous nickel sulfate in copper container. Is this clear? Students, is this clear?
Yes, sir.
If the value is less, you cannot store. That's the point you should keep in mind. Okay. Then reaction will occur or not. Okay. I'll add magnesium. I'll take magnesium chloride and I'll put copper. Can copper displace? Okay. Can copper displace magnesium into magnesium ion into magnesium? Is this reaction occur or not? Very simple. See the reduction potential of magnesium. I'll give you the value. The reduction potential for magnesium is I had the value. 1 second, student. Magnesium, yeah, magnesium is minus 2.37 volt, and for copper, 2 plus becoming copper, standard reduction potential values for copper is plus 0.34 volt. Now, students, tell me whether this reaction possible or not. Is this reaction occur or not?
No, sir.
Yeah, see here you have magnesium ion and here you have copper metal solid. Okay, right? If the reducing SRP of the metal, if it is lesser than the SRP of magnesium ion, then it will react. But here see that this value is positive, so that means this reduction potential is high. If metal has high SRP, see, metal has high SRP, that means it cannot displace this. Okay, therefore copper cannot displace Mg2 plus ion. Mg2 plus ion. Therefore this reaction does not occur. Okay, student, if I ask like this, try to answer this question now. Is this reaction occur? I'm just taking the reverse reaction.
Yes, sir.
Yeah. Now copper 2 plus, the reduction potential is positive. Okay, plus 0.34 volt. Whereas for magnesium, SRP value is minus 2.37 volt. Yes, magnesium has lower value. This reaction will occur. Magnesium can displace cupric ion into copper. Right? Are you able to follow, students?